Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome to the lecture on mechanical testing. We have been looking at basically all the basic mechanical testing and the results and interpretation. Especially in the last class, we looked at the high temperature tensile formation and activation energy and how it is applicable to other type of materials, especially the non-crystalline materials. We looked at even deformation kind of mechanism maps for the metallic glass and how the temperature and strain rate dictates uh, the mechanical aspects of deformations and so on. So in that connection, I just want to complete one more aspect of high temperature deformation called thermally activated process. So let us look at the important points in this. Plastic flow, especially at elevated temperature, can be considered a thermally activated process. The applied stress tau is opposed by variety of internal stresses whose sum is given by Ti. Okay, before even getting into the details, this particular aspect of what we are going to look at now in a few slides, which is also form a foundation for the high temperature deformation we are going to see in the next chapter. Right? For example, stress structure and creep test and so on, or creep deformation. We are going to look at them elaborately, even superplastic deformation and so on. So this is very basic. So in general, this plastic flow at elevated temperature is considered thermally activated process. So experimental study on the activation energy of plastic deformation and its the influence of temperature, strain rate, deformation, impurity, etc. Is again a primary activity of studying the theoretical models of deformation or explicitly a dislocation process which is involved in the high temperature deformation. So that is the primary idea. So in this context, the tensile test which is performed at very high temperature is directly connected to this. People have estimated the activation energy and then try to connect the dislocation substructures which is involved in finding out and then finding out the activation energy and so on. So I would like to just touch upon this aspect and then we can move on to the next topic. So I thought it will form a foundation. So the applied stress tau, that is shear stress, is opposed by variety of internal stresses whose sum is given by tau I. How do we understand this? So the effective shear stress is tau minus tau I. The internal resisting stresses can be grouped into two categories. One is long range obstacles to plastic deformation, which represents barriers too high and long to be surmounted by thermal fluctuation. And second, short range obstacles less than 10 atoms diameter for which thermal fluctuations can assist dislocation in surmounting these barriers. See, we have to just now understand these two classification before we discuss further. So what it says, a long range obstacles to plastic deformation. What is this long range obstacles? So basically the long range stresses which is caused by, it could be a dislocation, it could be a precipitation, or it could be a massive second phase particles and so on. So their contribution, okay. So in general, they don't get affected by the temperature and strain rate, except that the high temperature will result in the decreasing in the shear modulus of these constituents, right? So other than that, it does not have anything to do. So the contribution of this long range stress to the internal stress through the in terms of shear modulus, how much that is called tau mu, that parameter we are going to see. Okay. On the other hand, the short range obstacles. What are the short range obstacles? If you look at the stress fields come from the other dislocations, dislocation intersections, dislocation climb, dislocation cross slip, and intersection jogs and other things. These all will contribute to the short range obstacles, which can be easily surmounted by the thermal fluctuation. The previous one, in fact, the long range obstacles are all called thermal barriers, because the temperature and strain rate do not affect them directly. I mean, they are independent of the temperature and strain rate. And the short range obstacles are called the thermal barriers, because the thermal fluctuations will surmount this and then they will overcome this. Okay, so that is the idea of these two classifications. So if you look at this schematic, what does it show? This is an internal resistance versus the lambda. I mean, this is a shear stress, a long range stress, which is in the lambda, which will act in the lattice depending upon, act in the lattice in arbitrary orientation. And the magnitude of this long range stress depends upon the typical orientation, some other factors like that we know from the earlier definition also, right? The magnitude of the shear stress, it depends upon so many factors, right? So, so what is shown here is this is a long range stress, which is represented by the lambda, and then the small peaks, they are all the overlapping short range stress field. Okay, so you can see that the short range stress field, which is the magnitude is equal to tau naught, which is a shaded region above the applied stress tau. Okay, so for a given temperature, that means at the 0 Kelvin, the tau naught will be 0, because the thermally activated process is not there. So the applied the stress will be tau. But even if there is a small increase in the temperature, that will assist the tau in decreasing the tau. Okay, so even if you assume that small temperature increase and then that fluctuations helps to reduce the tau further, and then when it reaches tau mu, which is the shear modulus, which we talked about, then you can see that it will surmount all the barriers, thermal barriers, right? Thermal barriers, which will take care of all this short range stress field. See, you have to just bring back all the old concepts which we have already studied to connect this. If you look at this, what you are seeing on the right hand side, it's a force versus distance diagram. So exactly similar plot we have already seen, where we looked at what is the thermally activated process. Exactly, we have seen that it is the same plot, but we are just trying to address the mechanisms in terms of high temperature deformation, and we try to connect this with the dislocation substructure. That is the only difference. Rest all is the same. So the magnitude of this curve will depend on the direction in the lattice, that is what given here, and will vary with the plastic strain and the strain rate. So the total internal stress is given by tau I is equal to tau mu plus tau star. So the tau mu, the total internal stress which is resisting the applied shear stress is tau I. Tau mu is a shear modulus, which is given by all the obstacles of long range obstacles, and tau star is the short range obstacles like dislocation, climb, pulse, Nabarro force, and dislocation cross lip, and so on, so forth. So that is how we should understand this. So this is a total internal stress. So what we have to now understand is the following. Seeger has considered the short range barrier in detail for the common type of barrier where the activation energy not a function of tau star. This condition applies to the intersection of dislocations and movement of jogs. On the application of a stress tau which is greater than tau mu, so that means what? It is sufficient enough, this shear stress is sufficient enough to surmount all the short range or local short range obstacles. It could be a thermal fluctuations. A dislocation moves up the force barrier, which is shown in the previous slide, to a level of F is equal to tau B L star. So this particular expression is also quite familiar to us. So it is given in a slightly different notation, but the meaning is same. We have seen that tau B, F is equal to tau B is a very basic equation we have been seeing from the beginning, where B is a Burger's vector and L star is the length of the dislocation segment involved in the thermal fluctuation. So we are now concentrating on the dislocation segment, which is involved in the short range obstacle, the shaded region in the small peak, which is overlapped with the long range stress lambda. Okay, that is what it is. So delta H is the energy which must be supplied to overcome the barrier. The work done by the applied stress during the thermal activation is W is equal to tau star B into X naught star minus X naught is equal to tau star B B star. So what is X star minus X naught? I'll go back. So if you look at this force versus distance plot, so X naught is here, X naught star is here. So this is the distance we are talking about. So this is nothing but D. So this is the work done. So the work done by the applied stress during the thermal activation is this, given by this. That is tau star B D star. The term delta H is the area under the force distance curve. That is the total area under the force distance curve from X naught to X naught star, which can be also written as delta H star minus the work done by the applied stress during the thermal activation. So delta H is equal to integral X naught limits X naught to X naught star Fx minus tau star B L star dx, which is equal to delta H star minus V star tau star. Okay. So this is a very simple expression to visualize the activation energy, right? Thermal activation energy. The term delta H star represents the activation energy for zero applied stress. The term V star is called the activation volume. It represents the average volume of dislocation structures involved in the deformation process. So if you recall, we have used this term activation volume even in the deformation maps of non-crystalline material, that metallic glass, etc. We have used the term activation volume. There again, we talked about the dislocated region, the amorphous region that completely dislocated. That total area was calculated. Taken into account. Here it's a similar concept, but except that it is, since being a crystalline material, we talk about the dislocation substructure which is involved in that process. So that's the only difference, but the concept is the same. In terms of figure, we have seen that figure. V star is equal to L star B D star. So which is the hatched area, that is delta H, what we have shown in the previous force distance plot, which is you can relate this with V star, that hatched delta H star can be compared with this for a process in which L star does not vary with stress, In this relation, L star B is the atomic area involved in the flow process, and B star is the distance the atoms move during this process. So one of the most basic dislocation equations in the one relating shear strain rate with the dislocation velocity is this: gamma dot is equal to rho B V bar. This equation also familiar to us. We have, when we looked at the dislocation density, we have looked at this, and also some tensile deformation, we have used this. The strong temperature dependence of shear strain rate can be expressed as gamma dot is equal to A times e to the power minus delta G by kT, which is nothing but, if you relate these two, gamma dot can be rewritten like rho B S into V star into exponential minus delta G by kT. What are these terms? Delta G, the change in Gibbs free energy of the system, A, the overall frequency factor, and V star, the frequency of vibration of the dislocation segment involved in the thermal activation process. It's almost, we are saying that it's an activation volume. S is equal to the average distance a dislocation moves after every successful thermal fluctuation. Shoyak has shown that the activation volume V star is related to the above equation according to V star is equal to kT times dou ln gamma dot by A by dou tau at constant temperature, which is equal to minus dou delta G by dou tau at constant temperature. So this is one expression which can be experimentally found out. We can find out the activation volume through experiments, that is high temperature tensile deformation, and then you get these quantities. So that is why these two equations have been brought. So how do they find these quantities? People do a test, tensile test, and then create this strain versus time plot at constant temperature. Then you get these quantities, and then you can perform the test at constant strain rate. Then the sigma versus time plot will give these quantities, and you can also perform a constant stress test and then create this epsilon versus time plots, and then to derive these quantities. Okay, so this is a differential test to determine the deformation parameters at constant dislocation structure. This is an assumption. So these are the quantities which you can find out from the simple high temperature tension test, and then derive these quantities and then relate this with the activation volume. This is just a I just want to bring this because how do people find the activation energy, and then what is the meaning of activation volume, and how it helps in understanding the high temperature deformation. So that's why I just brought these concepts to this lecture. Okay.